NVIDIA can build faster chips. OpenAI can raise more money, but the AI race now depends on something none of them can download, scale overnight, or fix with a software update. Electricity. This is the physical wall hiding behind the AI boom. The companies that solve it may shape the next decade of technology just as much as the companies designing the chips. So how did power become AI's next bottleneck? And does it threaten the boom or simply change who wins? Start with the scale. The International Energy Agency says the largest technology companies spent more than $400 billion on capital projects in 2025. It estimates that spending could jump another 75% in 2026. That money is not buying an app. It is buying land, steel, concrete, networking, cooling, chips, and enormous electrical connections. The IEA says global data center electricity demand grew 17% in 2025. AI-focused data centers grew even faster, 50% in a single year. Its central projection has total data center electricity use rising from roughly 485 terawatt-hours in 2025 to roughly 950 terawatt-hours by 2030. That is about 3% of global electricity demand. 3% may sound small until you remember that the demand is arriving quickly and is concentrated in specific places. A country can add power gradually. A giant AI campus wants a city's worth of capacity at one address. And that concentration is the part most headlines miss. In the United States, Lawrence Berkeley National Laboratory estimates that data centers could consume about 11.8% of national electricity by 2030. Its modeled range runs from 9.5 to 15.3%. The range matters. Forecasting AI infrastructure is difficult. Some announced projects will be delayed, some will shrink, some will never be built, efficiency will improve, but even the low end represents a major change for a grid that spent years planning around relatively flat demand. Here is where the software world's sense of time collides with the physical world. A model can improve in months. A chip generation can move from design to production in a few years. A major transmission line, power plant, or grid connection can require planning, equipment, permits, construction, and political agreement across a much longer timeline. The grid is also more than a pool of electricity. Power has to travel through the right wires at the right voltage without overloading the system. A region can generate enough electricity overall and still lack the local transmission or substation capacity needed for a new gigawatt-scale campus. The Department of Energy's 2026 Draft National Transmission Needs Study says there is a pressing need for additional transmission because of new generation, new loads, congestion, and reliability. Several grid regions have responded by approving some of the largest transmission portfolios in their history. In other words, buying GPS is only the beginning. You also need a place where those GPUs can be plugged in. Now consider what 1 gigawatt means. OpenAI recently announced a 1 gigawatt data center campus in Michigan. A separate proposed project at the Savannah River site pairs a 1 gigawatt AI data center with approximately 2 gigawatts of on-site generation. The Savannah River plan is especially revealing. It proposes using natural gas as a bridge toward nuclear energy. The selection is still subject to negotiations, permitting, and approvals, so it is not a completed project. But the design tells us where the industry is heading. The data center and its power supply are increasingly being planned as one machine. Think about how unusual that is. A technology company is no longer just choosing servers. It is effectively choosing an energy system. Technology companies are starting to behave like energy developers. Meta has announced agreements intended to support up to 6.6 gigawatts of existing and new nuclear capacity by 2035. OpenAI's Stargate projects combine data center planning with energy, construction, financing, and community agreements. NVIDIA is working with energy companies on AI factories designed to coordinate computing loads, batteries, and on-site generation with the grid. This is not because technology executives suddenly developed a hobby for substations. It is because access to power is becoming access to growth. That creates a new geography for AI. For years, data centers clustered around fiber routes, customers, tax incentives, and existing cloud regions. Those factors still matter. But future AI campuses may increasingly follow available electricity. Regions with dependable generation, transmission capacity, industrial land, water-conscious cooling, and a workforce capable of building complex facilities gain an advantage. Regions with crowded grids and slow interconnections may lose projects even if they have excellent universities and strong technology talent. The AI map could start looking less like a software map and more like an industrial map. That shift could create new winners far away from Silicon Valley. So what powers it all? The honest answer is not one technology. Solar and wind can be built relatively quickly and paired with batteries, but an AI data center cannot simply disappear when the weather changes. Natural gas offers dispatchable power and faster deployment in some locations, but it carries fuel price and emissions consequences. Existing nuclear plants provide large amounts of firm power, while new nuclear could eventually add more. But new reactors still face cost, supply chain, regulatory, and construction challenges. The likely outcome is a mix: renewables, storage, natural gas, nuclear, stronger transmission, and better efficiency. Different projects will make different trade-offs based on location and timing, but there is a more surprising option: make the computing itself flexible. Not every AI task is equally urgent. A live voice assistant needs an answer immediately. Some training, simulation, data processing, and research workloads can shift in time or move between locations. NVIDIA and Emerald AI are developing systems intended to coordinate computing with batteries, on-site generation, and grid conditions. During a period of grid stress, selected workloads could slow or move while priority services continue operating. That turns a data center from a giant and flexible load into something closer to an active participant in the power system. It will not solve every constraint, and a company will not pause its most valuable service just because electricity prices moved for an hour. But even limited flexibility could help projects connect faster, reduce peak demand, and use existing infrastructure more efficiently. Now for the counterargument: AI is becoming dramatically more efficient. The IEA says the energy required for a simple AI task has been falling at an extraordinary rate. A basic text query can use less electricity than running a television for the same amount of time, so maybe the power problem solves itself. That is the strongest argument against this entire story. It is also incomplete. Except efficiency is only half of the equation. When something becomes cheaper, people often use much more of it. And the industry is moving beyond short text answers toward video generation, long reasoning, autonomous agents, scientific simulation, and always-on services. The IEA says some of those workloads can require hundreds or thousands of times more energy per query than simple text generation. The chips are getting better. The demand for what those chips can do is growing even faster. That is why the power wall is not necessarily the end of the AI boom. It is a filter. Projects with weak economics, speculative customers, or no credible path to electricity may disappear. Stronger projects will secure power, build generation, redesign workloads, and move to regions where infrastructure can support them. The winners may not be only model companies and chip designers. They may include the businesses that manufacture transformers, construct substations, manage cooling, develop generation, build transmission, and turn unreliable project plans into operating capacity. The least glamorous equipment in the AI stack could become some of its most valuable. But the biggest change is strategic. In the first phase of the AI race, advantage came from algorithms, talent, data, and chips. In the next phase, advantage may come from the entire chain that converts electrons into intelligence. The best model in the world cannot serve anyone if the building that runs it cannot get connected. So when you hear another announcement for a billion-dollar AI campus, do not ask only which GPUs it will use. Ask where the electricity comes from. Ask how it reaches the site. Ask who pays for the infrastructure. Ask whether the project can operate reliably. And ask what happens if demand arrives faster than the grid can expand. Because AI's next breakthrough may depend on a technology much older than artificial intelligence itself: the power system. What do you think becomes the real limiting factor? Chips, electricity generation, or the grid that connects everything together? Tell us in the comments. And if you want clear, deeply researched stories about the technology shaping the future, subscribe to Future Signal.